the Q-SE workshop. Before we start, actually, I want to actually mention that we are actually recording the session, the keynote, and also the presentations. If anyone here who doesn't want to get this recorded, please raise your voice through the chat room. Yeah, we will take the measures accordingly. Okay. So today, we actually have the privilege to have the keynote from Mingsheng about the verification of the quantum programs. So Mingsheng is the distinguished professor, also the research director of the Center of the Quantum Software and Information at the University of Technology, Sydney, Australia. So Mingsheng, you can take over the stage, so we can start now. Thank you.
Hello, everyone. So it's my great pleasure to give a talk at this wonderful workshop. So first of all, I'd like to thank the program committee for inviting me and for Tao's very nice introduction. So I'm going to talk about the verification of quantum programs. So this is the outline of my talk, a very brief introduction, and then I will introduce some base codes of quantum theory, and then define the quantum programming language, and then introduce this quantum Hoare logic. At the end of this talk, I will briefly mention the automatic tools and some applications. So why we needed this verification of quantum programs? In this two recent review paper, they mentioned that the verification is necessary for every stage of quantum computing, from programs to a circuit and also to hardware designs. Actually, in the last 10 years, many verification techniques of classical programs have been generalized to quantum programs, including program logic, model checking, and many others. But in this talk, we will focus on program logic approach, in particular, quantum Hoare logic, and some related issues like invariant generation and the termination analysis. So let's start from the base codes of quantum theory. I believe all you know the state space of a quantum system is a Hilbert space. For the finite dimensional case, it's just simply the space of complex vectors. And then the pure quantum state can be described by unit vectors. So we will use this Dirac notation, cat per psi, cat phi, to denote pure state. So here's the very simple example of a quantum state, a quantum bit or qubit. So the state space of a qubit is a two-dimensional Hilbert space. And then the pure state of a qubit can be written as a cat per psi equals alpha cat 0 plus beta 1. So you can see a qubit can be in a based state, cat 0 and 1, which corresponding to the values of a classical bit. But more interesting, a qubit can also in the superposition of 0 and 1, like the state plus and minus. So both of them are superposition of 0 and 1. In some applications, some situation, maybe we don't know exactly state of a quantum system, but we know this system is in the state of psi1 with a probability of p1, in the state of psi2 with a probability of p2, and so on. And then we will say this quantum system is in a mixed state. So a mixed state mathematically can be defined as an ensemble of pure state plus the corresponding probabilities. Furthermore, it can be described by a density operator. Actually, this was first suggested by von Neumann. So it can be represented by this matrix law, which is the summation of a pi, ket psi I, and bar psi I. So I guess all you know the ket psi I actually is a column vectors, and then the bar psi I is the conjugate transport of ket psi I. It will be a law of vectors. So ket psi I times bar psi I, then is an if the dimension of the system is d, and then it's a this multiplication of a ket psi I and bar psi I will be a d times d matrices. Let's see a very simple example, which is a mixed state of a quantum bit. So this qubit is in a state 0 with a probability 2/3, and in the state minus. I guess you may remember the ket minus is the superposition of 0 and 1. So the qubit in the state minus with the probability of 1/3, and then its density operator can be computed in this way. It will be this the 2 times 2 matches. So now we know how to mathematically describe a state of a quantum system. So we have this static description of a quantum system. Then what about the dynamics? So the dynamics of a quantum system can be a closed quantum system. I mean, a quantum system without any interaction with the environment. Then its dynamics can be described by a unitary matrix. So suppose the current state of the system is psi, and then at the next point of time, it will become u psi. So here u is a unitary matrix. Of course, we are considering discrete time. If we talk about the continuous time, then we need to use so-called Schrödinger equation to describe this dynamics. So here's a very simple example of a unitary matrix, which is Hadamard gate. So Hadamard gate is a single qubit gate. For example, if the input is 0, then after this Hadamard gate, we will get the ket plus. If the input is 1, and then we get the state ket minus. So you can see H transform the basis state to their superposition. Of course, we have many more unitary matrices or quantum gates like Pauli gates, rotation, and also we have multi-qubit gates like the C0, control knot. So control knot is a 2-qubit gate. It can be written as this in a matrix. the interesting thing for the C-knot is this. So C-knot can generate the entanglement. Suppose we have two qubits. The first one is in the state plus. The second one is in the state 0. And then after this C-knot, we will get the EPR pairs. So this is the maximally entangled state. But before the C-knot, we have this separable state. So this is the dynamics of closed quantum system. But if the quantum system is open with the interaction to the environment, and then the dynamics must be described by a super-operator. So if the current state is a low, which is density operator, it's a mixed state. And then at the next time, next point of time, the system will be in a state E low. So here E is a mapping from a density operator to density operator. Usually we call it a super operator, but it is required to satisfy some conditions like completely positivity. But here, I guess I should not go into the details of this, definition of super operators. Okay, so now we have, the quantum state like as an input, and also we have unitary matrix, unitary operators or unitary transformations as a gate, and then after a sequence of gate. So we get an output from the computation, but this output will be a quantum state. Then the question is how we can extract the information from the quantum system. So we want to get the classical information, meaning the information that human can understand. Then we needed to do this quantum measurement. So mathematically, a quantum measurement is described as a set of matrices, MM. So here we use this subscript small m to denote the possible measurement outcomes. There's a fundamental difference between the classical measurement and the quantum measurement. So for quantum measurement, we can have many different possible outcomes of the measurement with different probabilities. So essentially, quantum mechanical is a static. Now, suppose we have a quantum system in a pure state per sign before the measurement, and then the probability we get the outcome m can be computed using this the formula. So first we multiply this measurement operators mm with the vector, and then we take the square of the length. Then after we get this outcome, the system will be the state of the system will be changed from per sign to this new state. If the quantum system is in a mixed state, we have we also can compute this probability PM, and also this post measurement state. So this was giving as a basic postulate of quantum mechanicals. let's see a very simple example. So this is a measurement on a qubit in the computational basis. So this measurement can be modeled by two matches, M0 and M1. So this measurement has two possible outcomes, 0 and 1. If we perform this measurement on the qubit psi, which is alpha 0 plus beta 1, and then using the formula we just mentioned, and then we can see the probability of outcome is the square of the modular alpha, and the probability of the outcome is square modular beta. If we perform this measurement on a mixed state, like this mixed state law, and then we can compute this probability as the 5/6, and after after measurement, this system will be in the state 0 rather than the previous state law. So with this preparation, and then we can define the quantum programming language. So this is a very simple language for quantum programming. In this language, we even don't include the classical variables, but this is not a problem because classical computing can be encoded in the quantum computing. So we clean up this. We don't include this classical variables so that the theory become more the elegant and more simple. So in this language, we have skip. We have the initialization. So Q is a quantum variable. It is initialized in this base state. Because we cannot copy actually a quantum state, so we need this initialization, and then we have this sequential composition, the same as in the classical programming. So we first do this S1, if S1 terminate, and then we do S2, and then we have this unitary transformation U performing on a sequence of quantum variables, Q bar. So Q bar is in a sense, it's a quantum register. But perhaps the most interesting thing is the last two statement, if statement, or we call the case statement, and the while loop. So in this if statement, we have a quantum measurement M acting on quantum registers Q bar. According to the different outcomes of this measurement, we will choose different sub-programs to execute next. So suppose the outcome is M1, and then we will do SM1. If the outcome is M2, and then we will do SM2, and so on. There's a major difference between this quantum if statement and the classical if statement. In the classical case, after we checking the condition, the program state is not changed. But in the quantum case, because we needed to do this measurement, so after you check this condition, and then the program state will be changed. Similarly, in this while loop, we have also a measurement. But this measurement is a very simple measurement because it has only two possible outcomes, 0 and 1, or sometimes we say true or false. So if the outcome, the measurement outcome is 0, and then the while loop terminate, we exit the loop. But if the outcome is a 1, and then we must do this loop body S. After that, we enter this entire loop again. So this is the syntax of our language. And then we can define the operational semantics. We will use this configuration, which is the pair, S and the law. Here, S is a quantum program, or a special notation, $arrow. We use this $arrow to denote the termination. But also we have this law, which is the density operator. Actually, we will use the so-called partial density operator. A density operator is the semi-definite positive operator with a chase 1. Chase means the sum of the entries on the main diagonal of this matrix. By the partial density operator, we mean the chase can be strictly smaller than 1. Later, we will see why we need this, the partial density operator rather than, the ordinary density operator. Okay. Using this, the configuration, and then this operational semantics of a quantum program can be defined as transition systems using the following transition rule. The first rule is for skip. So suppose the current, suppose that the program to be executed is a skip, and the current state is a low, and within a single step, the program terminate, and the low, and the program state low is not changed. So still we have this low. So all you know what's the skip. But for the initialization, the things are a little bit different. So again, this program will be terminated within a single step. So Q equals 0 become termination, but the program state law will be changed to a law 0 Q. So the law 0 Q can be computed in this way. This again came from the basic postulation of a quantum mechanicals. If Q is a Boolean, the type of Q is a Boolean, meaning Q is the qubits, and then you got law 0 Q. If Q is an integer, and then you use this formula to compute this law 0 Q. You see here, for the Boolean case, 0 becomes 0, 1 also becomes 0. In the integer case, for all integer n, it will become 0. So this is the initialization in the base state 0. So the next rule is for the unitary transformation. So we do this unitary transformation, and then it's a step in the single step. It terminated in a single step, but the law is changed to a U law U diagonal. So here we are talking about the bigger step semantics, not care about the details of U. The unitary U can be a very large matrix. So the transition rule for the sequential composition is the same as in the classical case. So this one is for the if statement. So if the program is a if statement, and the current program state is a low, and then for each possible outcome M, if we do this measurement and get this outcome M, and then law will become MM law, MM diagonal. Next, we will execute this sub program SM. Here, I should mention that, we incorporated the probability of the outcome M into this program state, so that we don't need to put the probability here over this, the transition. Then we can use this ordinary transition system to describe the operational semantics. Otherwise, we need to use, probabilistic transition system. So in this case, we have this MM law, MM diagonal. The trace of this matrix will be can be strictly smaller than 1. So it's a partial density operator, not really, the ordinary transitional, not ordinary density operators. So this is the transition rule for if statement. So these two rule for the while loop. So L0 means if we wanted to execute this loop, and the current state is a low, and then we do the measurement. If the measurement outcome is 0, and then the law becomes M0 law M0 diagonal, and the program terminates. If the outcome, if the measurement outcome is 1, and then the state is changed from low to M1 low M1 diagonal, and then we must execute this loop body followed by this entire loop. So now we define this operational semantics. Based on the operational semantics, we can define the denotational semantics. Suppose we have a quantum program S, and then its denotational semantics is a mapping from a partial density operator to partial density operator. If the input is a law, and then the output is computed in this way, so we start from the configuration S and law, because using this program S, there may be some measurement, and the measurement can introduce a non-determinism. So there may be multiple different execution paths. Some paths may go forever, never terminate, but some paths will be terminated using a finite number of steps. And then we take this program state at the last step of this path, and put all this final state together, and then we sum up them. So then we get this output of the program. So this is the denotational semantics. Here there's a simple but important observation, which says the trace of the input is always bigger than the trace of output. So law is the density operator. The trace is the the summation of the entries on the main diagonal of this law. Intuitively, a trace law means the probability of the presence of the state law. So you see trace S law is smaller than trace law. Then the question is, what's the gap between this trace S law and the trace law? So trace law minus trace S law actually is a probability that the program does not terminate if the input is a low. We will see. We will use this observation later. So now we define this quantum programming language, and also its operational semantics and the denotational semantics, and then we can develop a whole style logic for verify the programs written in this language. As all you know, in the classical programming theory, we use a first-order logical formula to describe to talk about the properties of program state. But unfortunately, the quantum state cannot be simply described by first-order logic formula. In the 2006 paper, the Hong and the Panagadan suggested to use this Hermitian operator as a quantum predicate. So this is a very nature, the suggestions, because the Hermitian operator is a mathematical model of physical observables. Using this notion of a quantum predicate, and then we can introduce the correctness formula for quantum programs. So in a sense, it's a quantum Hoare triple. So a quantum Hoare triple, the appearance of this quantum Hoare triple is exactly the same as the classical Hoare triple. We have a precondition P, and at the middle, we have the program, and also we have this post-condition Q. But here, in the quantum case, S is a quantum program written in the programming language we just talk about, and then both P and Q are quantum predicate. Not the first order logical formulas like in the classical the Hoare triples. So we also call this a P as a precondition and the Q a postcondition. So a Hoare triple has two different interpretations. So we can interpret the Hoare triples in two different ways. In the classical programming, namely, we can talk about the partial correctness and the total correctness. In the quantum case, we can also define the total correctness and the partial correctness. So we say this Hoare triple PSQ is true in the sense of a total correctness if for any input law, which is a density operator, the trace P law is smaller than the trace QS law. Intuitively, trace P law is the probability that the input law satisfies this precondition P. And the trace QS law is the probability that the output S law satisfies the post-condition Q. For the partial correctness, then this defining inequality must be replaced by this one, a little bit more complicated. But if you compare this two inequality, you can find that the only difference is this, the second term, Chase law minus Chase S law. So you may still remember what's this. So let's go back to this observation. So Chase law minus Chase S law is the probability that the program S does not terminate. So then we see this Hoare chapter is true in the sense of a partial correctness. If input law satisfy this precondition P, then either the program doesn't terminate or it terminates in a state, in a final state, which satisfy this post condition. But of course, here we are talking about the probabilities. Okay, so this is the partial correctness and the total correctness for quantum programs. Fortunately, we are able to develop logical systems, proof systems for verifying the partial correctness and the total correctness. For the partial correctness, the logical system consists of 3 axioms and also 4 inference rules. So the axiom for skip is the same as in the classical case. The axiom for the initialization is different, is given in this way. Or I would skip the detail of this. And also where we have axiom for the unitary transformation. So this inference rule for sequential composition also the same as in the classical case. But the rule for if statement is much more complicated than the classical case. Perhaps the most interesting thing is this, you know, the rule for while loop. If you compare this rule with the Hoare's rule for classical loop, we will find some interesting difference. In the classical case, if we look at the premise of this Hoare's rule, you will find that the precondition is more complicated than the post condition. But here you see the precondition is simple, the post condition is more complicated. But they have a very good, you know, the symmetries. So this is the, you know, the Hoare proof systems for partial correctness. Then we can prove this completeness for our logical system, which says for any quantum program S and for any precondition P and the post condition Q, if P as Q is true in the sense of a partial correctness, and then it always can be proved only using this 3 axioms and the 4 rules. You know, we have many quantum programs. Actually, we can have infinite many quantum programs, but it always can be proved only using this as 3 axioms and the 4 inference rules. So this is the completeness theorem. Of course, this completeness is only a relative completeness relative to the accession logic about the precondition and the post condition. For example, here we needed to use this the theory of complex number. So this completeness is only relative to the theory of complex numbers. For the total correctness, we also have a proof system, but this system is a little bit more complicated. I guess I should skip this details. And then the only difference between the proof system for total correctness and the proof system for partial correctness is the inference rule for while loop. because we needed to use this linking function to guarantee the termination of our loop. Or again, we have this completeness. But this time, the completeness is relative not only to the series of complex numbers, but also asymptotic analysis, because in here we needed to use a kind of limit. I guess I should mention that the proof of this completeness theorem in the quantum case is quite different from the proof of the completeness for classical programs. Because in the classical case, we only need the tools from discrete mathematics. But for the quantum case, we needed to use tools from continuous mathematics. We needed to consider the convergence of infinite series of the operators in the Hilbert space. If you are interested in the details of this logic and also the completeness theorem, and then you can look at my paper in the Topology 2011, which was which is the go back to 2011. It's quite old papers. So now we have this the quantum Hoare logic for verification of quantum programs. Then the question is, can we build some automatic tools? A group at the Institute of Software, Chinese Academy of Sciences, implemented a CLM proof for quantum Hoare logic based on the Isabella. If you are interested in these tools, you can have a look at this, the web page. But there's also a paper describing the details of this CLM proof, which was presented at the CAFE 2019. In this CLM proof, the assertions, I mean, like a precondition, post-condition, and the intermediate assertions are given by human to the proofs, to the tools. So in a sense, this CLM proof is an interactive proof system. So then the question is, can we automatically generate this invariant? In a paper in the POP 2017, we proved this problem of invariant generation for quantum program can be reduced to an SDP problems, so and semi-definite programming problems. We also use SDP Sowell to deal with this, some interesting examples. The first example is a quantum random walk. Of course, we consider the quantum random walk with the absorbing boundary. If a quantum walk without absorbing a boundary, then it's simply a for loop. But a quantum random walk with the absorbing boundary, then it's a while loop. So we can use this SDP Sowell to generate the invariant for this quantum loop. But also we use it to find the invariant for a quantum algorithm called quantum metropolis sampling. It is an algorithm to find the ground state of quantum systems. Another related question is a problem is can we, I mean, for some time, for some application, can we automatically determine the program is a terminator or not? We prove this synthesis problem of a linear function for quantum program can be reduced to the to an SDP program, to an STP problem. But of course, we can only do this in the finite state space. Otherwise, holding problem become solvable. So we can only do this for in the finite dimensional space. Again, we have some examples. The first example is also the quantum while loop, but the second example is a quantum penurious factory. So this is a quantum penurious factory is a quantum algorithm for the the random number generation. Random number is widely used in the security and the protocol. Quantum penurious factor can generate some random numbers which cannot be generated by the classical the algorithms. So so this is the automatic tools for verification of quantum programs. Finally, I'd like to mention a couple of applications. The first application is reasoning about the NISQ program. So NISQ means noisy intermediate scale quantum. So it's a term invented by John Pascal. So our quantum logic can be generalized to a logic which can be used to reason about the Epsilon robustness. So Epsilon robustness means the distance between the ideal program and the error programs. So this this robustness logic was giving in this reference 8 and the reference 9. In a paper at the PLDI 2021, a research group from Columbia University and the University of Chicago implemented an automatic tools for the error analysis of quantum programs. But actually, in this tool, they can only deal with the program's result while loop. So for while loop, this problem is still the open. Another thing I like to mention is the local reasoning about quantum programs. In a quantum Hall chipel, both the precondition and the postcondition are very, very large matrix. If the quantum program has like n qubit, and then the precondition and the postcondition are 2 to n times 2 to n complex matrix, so they are very difficult to compute, to manipulate. So then we consider to introduce this idea of separation logic to a quantum case, meaning can we reduce this global reasoning to local reasoning using a kind of so-called the formation rule. Use this idea, combined with our quantum logic, we even discover a flaw in the Google's SIC tutorial for the VQE. So the variation of quantum algorithms. If you are interested in this, the examples, you can look at this our new papers in the next 2021. The next application is a testing and the debugging of quantum programs. I guess this audience will be more interested in this. So in this work, we choose to use a very special kind of quantum predicate, which are projections. So projection actually was used a long time ago by Beckhoff and von Neumann in their quantum logic. But for our case, we use a projection because the quantum measurement corresponding a projection can be designed only change the quantum state slightly, not too much. So that's why we use this, the quantum predicate as our runtime accession for testing and debugging. Again, in this work, we cannot deal with the while loop. So how we can, the dealing with this while loop is also an open problem for this, for the testing and debugging. So finally, I would like to mention this verification of quantum crypto security protocols. As you know, the original Hoare logic was designed for reason about the correctness of single programs. But in 2004, Benton proposed this relational Hoare logic for reason about not the correctness of single programs, but the relation between two programs, like the equivalence of these two programs. So later, in 2009, Gersbach and some others generalized this relational Hoare logic to probabilistic relational Hoare logic. And then based on it, they implemented an automatic tools called EasyCrypt for the security verification of cryptos. Because in the security and the cryptos, we always need to use this random numbers. That's why we need this probabilistic relation Hoare logic rather than the original relational Hoare logic. Then in 2019 and also last year, Dominic and Lu and Gersbach and some others extended this relational Hoare logic to a quantum relational Hoare logic, and also use it for the verification of security of quantum one-time pad. So quantum one-time pad is the quantum counterpart of this crypto protocol one-time pad. So this is my talk. Thank you.
Thank you so much, Mingsheng. Thanks for a wonderful talk.
So I can stop the sharing the screen, right?
Yeah, you can stop, or we can actually wait for questions if you.
Okay, good.
Yeah. So any questions from the audience here? Actually, I see. Mingsheng, if you can see there is actually a question from Ina actually in the chat room. If you click the chat room.
Right. So the question is, how does the proof rule of a while loop compare to the invariant rule of classical logic? So you mean this? So you are talking about the proof rule for while loop in the classical Hoare logic, right? So let me go back to this slide. So you see this rule for the quantum while loop. In the classic case, let's consider this while loop. While B do S. So in the classic case, B is the loop guard. It is a first order logic formula. But here in the quantum case, this loop guard is replaced by a measurement performing on a quantum register Q bar, and then we check the outcome is 0 or 1. For the classical while loop, where B do S, the precondition is B and say phi, and then the post condition will be phi, right? But here the precondition will be phi, and the post condition will be phi and not B. So you know that at the first glance, you will see quite the big difference between this while loop, this inference rule for while loop, and the classical rule for while loop, because in the classical case, this precondition is more complicated, which is the B and the P. And the post condition is a simpler, which is a P. But here in quantum case, precondition is a Q, much simpler than this post condition. But the idea behind it is behind this the quantum Hoare chapter is the post condition. I mean, and the precondition actually is the restriction of this post condition on the subspace corresponding to this the measurement operators M0. I'm not sure.
Thank you, Mingsheng. I guess we can actually, if Ina want to discuss more, I think Ina, you can either talk by yourself or we can do this offline. I see that Lakom raised hands as well, so we can give the opportunity to Lakom. You can ask the question now.
Right in the beginning of your lecture, you said that the choice, two possible choices for verification are logic approach and model checking. And
yes.
Your choice was logic. Can you explain why and compare with the alternative model checking?
Okay, so actually, model checking for quantum system, there's quite a lot of work on this, the model checking for quantum systems. This line of research was initiated in 10 years ago. The first application was the verification of quantum communication protocols. My choice to, my choice to only talk about the program logic because, I have been working in this area mainly. So, but I also did some thing about model checking. Actually, just few months ago, I published a book about the model checking of quantum systems by with the Cambridge University Press. So if you like, you can you can find it online. So
my question was, can you explain the choices, the advantages or disadvantages of logics compared with model checking?
Okay. So actually, the difference between the program logic and the model checking in the quantum case is similar to the difference between them in the classical case. For example, the model checking can be used to not only verify verify the correctness, but also can be used to find the bugs. But logic can only be used to verify the correctness, but not used to find the bugs. This is I guess that one of the most important difference between them.
Thank you.
Good. Thank you.
Yeah, I think that we finished this keynote session now because we already have 5 minutes for some of you to get coffee or lunch. So thank you so much again, Mingsheng, for the wonderful keynote. And for the others, we will actually resume in like 5 minutes, right?